Now let's move on to section 7.2, anaerobic metabolism. We're very human-centric, right? I mean, we always think in terms of life being humans, and we know clearly that there's more diversity on the earth than the human species. So anaerobic metabolism is used exclusively by many bacteria, for example, who actually die in the presence of oxygen. You know, when we often say, well, what constitutes life, or what's a requirement for life, students will often say, well, oxygen is a requirement. Well, that's not actually true. Oxygen, in some cases, can actually be a toxic poison. But during times of oxygen deficits, let's say during vigorous exercise, for example, where your body is working hard to, your heart is working hard to transport that oxygen-rich blood, there may be times when there's just not enough oxygen available to continue to supply the ATP for your muscles to continue to function. Or in some cases, you can lack oxygen entirely. For example, bacteria of the human gut often face periods where oxygen levels can be low. For these organisms, and for these cell types more importantly, they've devised strategies to be able to withstand these transient, sometimes transient oxygen deficient environments, or in some cases permanent oxygen-free environments. Two ways which we're going to see this happen today, fermentation and anaerobic respiration, both use alternatives to oxygen as the final electron acceptor. Remember, the electron transport chain is dependent on oxygen in order to keep everything flowing. If oxygen is lost, or oxygen's not available, the ETC stops, backs up. There are two consequences. There's one forward consequence and one backwards consequence. Let me start with the forward consequences here. When the ETC stops, the H plus gradient dissipates. Right? I'm no longer going to have the energy to create a gradient if the electron transport chain is no longer running. And if the H plus gradient dissipates, well, of course, we know on the very end, ATP levels are going to drop precipitously because we're not making any new ATP through oxidative phosphorylation. So that's the forward effects of not having oxygen. But that also causes a backward effect as well. If the ETC stops, what happens is NADH is stuck in its reduced form. Right? Because the only way to regenerate NAD plus is to oxidize that NADH. Well, listen, if NADH is waiting for the electron transport chain to free up and it never happens, well, NADH is stuck. Now, that's a real problem if you think about it, because if we're stuck in the NADH form, there's going to be problems within 3 reactions of the citric acid cycle. So the citric acid cycle is going to stop. Pyruvate oxidation requires NAD plus to function. So now we get backed up there. And if you think about it, step 6 of glycolysis required NAD plus as well. Without step 6 of glycolysis, if you go back and look, there is no substrate level phosphorylation. There are no 4 ATPs produced. So in the absence of oxygen under those conditions, we go all the way back to glucose. No energy is harvested, no energy intermediates made, and as you would imagine, a cell without energy intermediates is a dead cell. So what we have to do is either find ways to get the ETC kick-started again, or at least find a way to get through step 6 of glycolysis so I can have that minimum number of 4 ATP generated, 2 ATP net, in order to withstand these oxygen-limiting environments. So the first example is anaerobic respiration. In anaerobic respiration, the chain still runs. Glycolysis, pyruvate oxidation, and many of the reactions of the citric acid cycle continue to happen. And the reason that all of that can work is because alternative enzymes are inserted into the chain that are able to reduce other electron acceptors. Here's an example of E. coli under anaerobic conditions, still producing ATP despite that oxygen deficiency. And the way it can do that is it can use nitrate as the final electron acceptor due to the enzyme nitrate reductase. Complex 1, complex 3, complex now 4 is the one that's different, the one that reduces the final electron acceptor. And what this allows for the continuation of an electrochemical gradient. Now what I will tell you is that it doesn't create as steep of a gradient. And because the gradient's not as steep, there is less ATP per glucose generated by anaerobic respiration. Doesn't mean no ATP. It just means there's less ATP due to a less steep gradient difference across the inner mitochondrial membrane. So that's one strategy. The other strategy I'm going to spend a little bit more time on: fermentation. Fermentation has been exploited for thousands of years. Goes back to, I want to say 1500 BC, where the first signs that humans were able to ferment in order to create alcohol, for example. And so fermentation is really driven by an alternative to aerobic cellular respiration. In the case of fermentation, only glycolysis is able to run. And instead of using oxygen as a final electron acceptor, pyruvate and pyruvate derivatives, organic molecules, serve as the final electron acceptor. Now the benefit here we're going to see is we're going to free up NADH back to its NAD plus form in order to allow glycolysis to continue. And as long as glycolysis continues, I can still get a small amount of ATP for every glucose that enters glycolysis. And while that's not a great yield, especially when you compare it to aerobic respiration, for limited amounts of time, for certain cell types, that ATP generated through glycolysis only is enough to allow for continuing function. So for example, in muscle cells of the human body, fermentation could take place. Yeast cells carry out fermentation. A whole host of bacterial cells can carry out fermentation as well. Here's what it looks like. I had to Photoshop my face off of this because I didn't want to embarrass myself and show off my guns. But here's a nice example. Strenuous activity. Heart is pumping to try to replace the oxygen that's being burned up as we continue to make ATP to support muscle function. At some point, oxygen's not being delivered fast enough. We're going to switch the fermentation conditions. The pyruvate that's produced as a result of glycolysis is now acting as an electron acceptor. It is now being reduced in the process of fermentation. Why is it being reduced? Because it's working to oxidize NADH. And as NADH is oxidized, NAD plus is regenerated, which then goes to step 6 of glycolysis, which allows for the continued production of small amounts of ATP. Now during this reduction step of pyruvate, the muscle cells are going to produce lactate. Now, we've heard of lactic acid buildup in your muscle cells. It results in that burning sensation, the muscle fatigue that you feel. And if you think about it, man, that makes a lot of sense. If I have a big buildup of lactic acid in my muscles, that means I'm really working at an oxygen deficiency. There's only so long that muscle can continue to function with such little ATP coming out of glycolysis. So at some point my muscle's going to give out in order to give my body time to catch up, in order to restore those oxygen levels. So that's one example, lactic acid fermentation. Ethanol fermentation is the other. In this case, it's a two-step process. Pyruvate is decarboxylated. We lose a carbon dioxide to form an acetyl molecule containing 2 carbons. That molecule is then reduced as a function of NADH oxidation, which then regenerates the NAD plus that's so sorely needed for glycolysis. As a result of the reduction of this 2-carbon molecule, ethanol is produced, And we know that ethanol serves as the basis for beer and wine production.